for more than 2 decades.
We met, I think, in 1998, because that's the last year I was
That's right.
in
We were
Max
close
Planck
up.
Institute,
Yeah, we were close up to the same group. Okay. Thank you, Stephen Brandt.
Okay, so it's not necessarily easy problem to talk about. Anyway, so I'd like to talk about the Einstein Toolkit at LSU and the work that we've been doing there for the precinct project, which was these changes to the scheduler that have been talked about. These changes to the schedule aren't necessarily exactly what was originally planned. When this was written, the notion was that everything written as data dependencies, and it would sort of flow in a functional way. There are a lot of conceptual problems with doing that as a whole paradigm for Cactus, but what we focus on to start with is a thing called is the synchronization. Now, it looks very simple when you first hear about it, when you hear about synchronization in Cactus. You schedule a function and you write, sync at the end of it and tell it what you want sync, what grid functions you want ghost zones to synchronize on. And it sounds simple until you actually go to program something with it. I had the experience of porting a ghosting code into the Cactus framework, running that simulates the Boost-Nest equations, if you've heard those. And the thing I found was getting the synchronizations right was very difficult, right? So I probably should have had this slide up already. So the problems that you have is if you under-synchronize, right, then you get the wrong answer. And if you over-synchronize, then you waste all kinds of time doing communication, and usually wind up over-synchronizing in some sense just to be safe, because you don't know where you're doing it, and these kinds of things. The other thing that I realized was a related problem were the boundary conditions, right? The physical boundary conditions that you put on your grid. And even though ghost zone synchronization and boundary, filling in physical boundaries is conceptually the same thing, right? It's filling in the edges of the grid so that you can do your stencils. They're implemented in entirely different ways in Cactus. And they don't necessarily happen at the same time. And so what we're trying to do here is we're trying to unify these two operations, have them happen at the same time, and happen on demand, that is, when they're needed. And the idea is you shouldn't have to specify when these things happen. The system should be able to figure it out. And the basic concept is that you have read and write directives in the schedule tree. So when you schedule your functions, you say which grid functions are read and written. I'm just using Cactus terminology here in the hopes that you all know what I'm talking about. So when I talk about a grid function, right, this is a distributed data structure that goes across all the processors. And each processor owns a piece of it and has ghost zones which connect it to the others, right? So what you do is you identify which grid functions you're reading and which ones you're writing, and whether you need the data whether you read the data everywhere or just inside in the interior, or whether you're writing the data everywhere or just in the interior. And the basic idea is when you have a write to the interior and followed by a read everywhere, you need a sync. You need those boundaries filled in. And the system can detect that automatically if you tell it where to read and write. Now, that's fine, right? But the problem is you can put these annotations in the schedule, but then you have a new problem of how do you know that the annotations in the schedule match in any way what the code, what the functions that are being scheduled actually do, right? It would be easy, I would think, with no checks in place to get that wrong. And in fact, I would think that would be the default. And then there's some complications, right? Some routines are designed to read and write different things depending on the values of parameters. And then there's the prolongation and restriction operations of AMR, which interact with the grid in odd ways. Okay. So we did our best to implement this, and one of the things that we did that's kind of, that sounds kind of, well, you know, if you're fussy and you're OCD, you won't like this, right? So if you write to the interior, right, then we invalidate the exterior region, because we assume that when you're writing that area, you're intending to do that. On the other hand, if you write a boundary, we don't invalidate the interior, because we're assuming that you're just writing a boundary function and you're just applying it in an ad hoc way. There's not a beautiful consistency feel to that, but it sort of matches the way the code is. Okay, so I told you that our solution to read writes needs a solution to match the reads and writes inside the code. And what we came up with was the normal way of writing code in Cactus is you have this declare CCTK arguments macro. And what we did was we wrote some fancy Python code to generate a different macro for each function name. So instead of saying declare CCTK arguments and getting read-write access to all the grid functions, we use this macro, and it only gives you access to the grid functions that you declare. And if you declare those functions as read, then it gives you read-only access. It makes a constant array if you're using C++ or C, modern C. So, so in addition to this, we can do some other things. We can do a runtime check that the correct macro is called. So you can imagine somebody creating a bug, right, where they declare they don't have a match of the function name to the function that they're actually in. Maybe they have one character different. Maybe the function names look similar or something like that. We could potentially correct that. The other thing that we could do is if, oh look, there's a typo. If we say that we're writing a function and not reading it, we could invalidate. We could write names in there to help make that clearer to the result. So there's still some kinds of checks that we can do that haven't been done with regard to that. We also have, as a debugging mechanism, which you can enable, if you try to use a function that you shouldn't have access to, we can give you a null pointer there. And null pointers are usually triggered, null pointer exceptions are usually triggered quite easily when they happen. And then when you see one, you say, I probably got a declaration wrong. We also do some checksums to detect regions, which regions of the grid are modified. This is slightly problematic because there are some functions that are writing the interior, but just sort of do things in parts of the boundaries because it's more efficient for the code to do so, even though what's being put there isn't necessarily right. So there's all kinds of trickiness, as you can imagine. So one of the things that we wanted to make sure that we had was the possibility of disabling this feature and getting the old functionality. So the goal is, if you want to use things the old way, you shouldn't be stopped. We probably are not going to be able to make every single thorn function with this framework just due to time and budget considerations. But and so in that case, we want to allow some backward compatibility. So here are a list of the arrangements affected by this change. So it's lots of things. Most of these things are just correcting the schedule tree, just putting in the reads and writes in the correct ways. And this just represents, and most of that represents an ongoing effort to try and get that correct. Carpet is the primary thorn affected. Most of the logic is in a new file called precinct.cc. The feeling was that I had is that the more code I could keep in an independent file, the better off we'd be, because while this work is going on, right, all these different arrangements are getting modified, and I have to do git merges. I have to keep doing git merges just to avoid wandering off into no man's land. So we did that. Call function.cc is the most impacted function if you know Carpet or if you care about it. The flesh is probably the second most impacted. So one of the things that the read-write directives are currently available in the flesh an array of strings, which aren't parsed. And so we add some code in there to parse those, and we implement some of the checks we talked about. Cactus numerical, mol, in particular. Oh shoot, I didn't take my soda. I've got a bit of a cough, just a minute. I went to a water park and came back with a cough. Okay, so this is a technical detail you might not care about, but mol had to have two small modifications just to update the way it does things. I thought I'd show you the code in case you care about such things. Basically, these are very small changes, and the idea is we can find out, which past functions you're using to update the right-hand side of an equation, and we can use sort of a minimal mask, whether you're updating the interior or the whole region, and figure out what the updated region should be. And we can figure that out automatically, or automagically if you like, from Cactus, because we can find all your right-hand side functions using this mol built-in function. And the other function looks like that. So, what have we got working so far? So this represents an Einstein Toolkit build without Pug enabled. And in that circumstance, we have 53 of the tests in the test suite pass. We have 25 tests that pass to tolerance, so that's still passing. And then we have 43 tests that actually fail. If you look at it that way, that sounds really great. Unfortunately, AMR is one of these things that is really the problem. It's sort of spotty at the moment, and is also the most important thing. So there's clearly a significant amount of work left to do. The work has been done by myself, graduate students Sam Cupp and Roland Haas. We've all been sort of pitching in on this. Here are some results. I'm sorry about the blurriness of the plot. But what this is showing is that we've got, some of the codes that we have in the toolkit. You can run little benchmarks with them, and you discover that we do see a savings of time because of fewer synchronizations that we need to do. On average, there's like 5% less synchronizations in some of the tests we've looked at, and runtime improvement is between 5 and 20%, depending on a host of things, right? What problem you're doing, whether you're running across multiple nodes, and so on. We have some write-up of this will be given at the PERC 19 conference, which is the Exceed conference. You can use Presync today. I would encourage anyone who's interested in trying this out to go to this GitHub repo. Of all the people in the room who I hope will do this, I pick Zach. Because one of the things that we're going to want to have is we're going to have his norms, his hybrid norms and everything, work with this framework, and I think that he's the best person since they're his norms, to help make this work. And I think that could be a big step forward for this project if we can find time to get together and work through this. Okay, so we'll switch gears a little bit, and this isn't even about Cactus. This is about the solid force code, and I asked Peter Diener to give me some slides about this. So I'm not deeply familiar with it, but with his code. But what the concept was when we formed the Einstein Toolkit, right? The concept was that it wasn't supposed to just be Cactus. It was supposed to be a place where we could have a family of related codes. And that's never happened. But we're looking at, hopefully before the next release of Cactus, making that true. And we'll make that true by putting Peter's self-force code in there. And it's developed for every situation, the extreme mass ratio in spiral. By the way, I'm just going to take this opportunity to complain about the names Emery and Emory. I mean, they sound almost the same, and if you have a slight accent, no one can tell which one you're saying. So, all right. An Emery system, right, consists of a compact object orbiting around a supermassive black hole, and the object emits waves that propagate in the curved background of space-time. Some of the waves will backscatter off the curvature and produce the self force that drives the in-spiral. The force depends in principle on the entire past world line of the compact object, and the code should be able to perform evaluations for orbit and field are all together in a self-consistent way. You know, most importantly, right, if you tried to run, if you tried to set up such a problem with the current Cactus Einstein Toolkit, you would need huge grids. It would run forever. We would all die of old age before it finished, right? So, I mean, if it even could, right, because you'd have to constantly be checkpointing and restarting and whatever. So, currently, the self-force code solves the scalar wave equation in a Schwarzschild black hole spacetime, and they have perturbations as well for the Kerr spacetime in development. Fields are decomposed into spherical harmonics, so they become 1 plus 1D partial differential equations. Discontinuous Galerkin methods are used because all toolkits use discontinuous Galerkin methods now. For discretization, the code is highly accurate, exponential convergence thanks to DG. The code is written in modern Fortran because Peter is a Fortran guy. And, you know, we respect all lifestyle choices. It uses SCOMs for building, which is a different build system. It's a Python-based build system, and Ford for code documentation. So we hope that this will be, as I say, we hope this will be part of the Einstein Toolkit soon, and will extend the codes that are in the code base. And it might be nice if there are still other codes that you can include. And if anybody has any thoughts about that, I'd like to hear it. Anyway, so that's it. How did I do on time?
I think you did very well, and I have a question for you.
Okay.
So you're going to release it soon, you say, and we'd love to hear about comparing the results from this to existing codes based on wave equations, for example, Roger Wheeler or other type of code, concrete, so on.
I'm not sure what the question is, but
So the question is, has the code being applied in physical context, and have comparisons been made so to existing results in Emory?
so I can't really answer that very well. That's a question for Peter. It does say in here that it currently solves the scalar wave equation, so I think that's.
Okay, so it's the scalar wave equation. Okay.
So, can you just describe, and I think maybe I know the answer, but what does it mean for the code to be within the Einstein Toolkit, and what are the implications? How do you decide whether it is going to be supported as part of that? Can you just summarize what the current state of the art is?
Sure. Some of those questions are a little fuzzy. The answer to some of those questions are a little fuzzy. Currently, the Einstein Toolkit is going to be those codes that are mentioned together on the EinsteinToolkit.org website. They will, in principle, have the same release name, right? So we'll have the same release name for versions of all the codes on there. Whether they will be checked out together by default is an open question. But we'll have those kinds of things in common.
So they'll be tested on the same platforms, and they'll need
So yes,
If somebody's interested in making their code by the Einstein Toolkit, like what is the
Right.
barrier to entry? And
So-
do you take all codes, or are you only interested in ones that are going to be heavily used?
so most of the, we don't want codes that aren't going to be used. But ones that are heavily used are obviously more interesting. And things that cover different parts of the Einstein problem space are more interesting. We're going to want similar kinds of documentation conventions and testing procedures. So Cactus comes with a test suite, right? A regression test that is fairly extensive and covers a large fraction of the code base. We would want a similar test mechanism. We would want a good regression test mechanism in there. It would also mean that bug tracking would be through the common website and so on.
And as part of putting the code there, does Peter then, is he available to answer questions that come up? Or how does that
Well, Peter is on the users list, and it should be the case that if you have code in the Einstein Toolkit and your users have problems, they should report it to the users list, and whoever is able should answer them. So.
And of course, there should be also advantages from the people who are willing to, put their code in the Einstein Toolkit, taking advantage of the fact that we have a community of 244 users so far, 38 countries, and
I don't have those statistics off the top of my head.
well, I just
but-
got them from Roland.
Okay.
So if you want your code to be useful and used by and enlarged in the community, I think this is a great platform as you are exposed to having more and more users, of course, and
It's good for
just more
advertising.
advertising is also the fact that you have some quality control by having more users, and passing all these tasks. And I think that's an important aspect if you're in the business of producing.
I guess another thing that I could add in this same vein is that the Einstein Toolkit is interested in open codes. We don't want, if you want to have your secret code that nobody can read, that's probably not going to be something